in the previous part, we've set up the mesh for this FPV frame analysis. And if you haven't watched the previous part, please go back and watch it. I am a mechanical engineer by my background. I lead complex projects for new product design and mentoring engineering team for design thinking. So this is part of my initiative to expose free open source finite element softwares, as I think that performing finite element analysis on a basic level is a skill set that any mechanical engineer should have in his skill set. So let's continue this analysis. Okay, so next thing on my list is, well, first of all, how do I plan to perform this analysis? And what is the actual system like in real life? Because in the real life system, we have the flight controller here, the camera over here, the VTX over here, the battery, etc., etc. And so there's a lot of additional stuff that goes on top of this system, but we don't want to mesh those, and we don't want to use those in the calculations, because then it's going to create us a lot of problems. So the first thing after meshing, it will be adding those elements that represent more realistic system. So first thing what I would do is just add the point in space. I can place it in in between, like points, on a point, and center of gravity, or whatever bounding box. But for the sake of this analysis, I will just my assumption it's gonna be like maybe 30 millimeters. I'll just put it on 40 millimeters. This looks good enough. And naming is always good, because it helps me go back and understand what I did. And this is like the battery mass. And now what I like to do is like look at the design itself and say, okay, so how I'm going to perform this analysis. I know for a fact it needs to be fixed somehow, because analysis has to be fixed. Since the motors, they're the ones who will provide the forces, it wouldn't make sense for me anyway at this point, like to fix those areas and just apply loads to everything else and study, because these are the areas that actually create the forces. So what I would do, I know for a fact that the center of gravity is somewhere in this area. So what I will do is I'm gonna fix this surface over here. Maybe it's too big, maybe it's too small, but we'll see the results. And again, I'm less interested in this area for the analysis. I'm interested in about the natural frequency of the system and how those bending forces are going to be on the arms. And this is an assumption at this point. My assumption is these are the areas we're going to see higher loads. So let's start by creating surface names. It's going to be easier for me later on to apply those fixes, loads, by just using those names. And by doing so, I'll just create surface name. Let's say fixed center, for example, and I will select surface by angle. Yeah, it's fine. This side and this side. There can be always criticism about how you set up the boundary conditions. In most professional cases, before, if you're like a highly professional finite element expert and part of a team of experts, most likely this phase done as part of like a design review, because you're sitting with the other people and brainstorming about how you create those fixes, the loads. It's always a good idea for everything, even for conceptual design. You complete this phase and you share this vision of yours with your colleagues. There's always something to learn from others. At this point, what I need to do now is adding those surface areas for where I'm going to apply the loads. So what I'm going to do next, I'm going to create the surface for, let's say, motor 1 load What's next? So we've created the battery mass point. We've defined those surfaces for the loads. At this point, what we're missing is, of course, the materials. And this is also something that's very important. Why is that? Because if you don't have the proper properties of the material, then you're going to end up with, the simple terms, garbage in, garbage out. Now, this is interesting. Why? Because this analysis, and this is why I'm saying is I like to do this more practical stuff, real life things, because, someone can come to you and say, I want to analyze, like, this is a carbon fiber part. So this is not an easy analysis. And this is where, as an engineer, since, again, we are not the experts for finite element analysis, we are engineers who would like to design something and understand how it's going to behave and react to forces. Therefore, we are allowed to make assumptions. And this is important to make those assumptions because this is, again, going back to design thinking. This helps us simplify the problem. Because, if you try to scratch your head and say, oh, this is carbon fiber part, how am I going to analyze this? Because it's layer by layer, it has epoxy, it's a composite, a lot of details. But the thing is, again, we would like to get higher level understanding of the distributed forces and whether our design can comply or not comply with those requirements in a certain level at this point. So therefore, I just created a composite material and I added all the relevant information that represent a composite material with a few assumptions of a mixture of the properties of epoxy and the carbon fiber itself. And these combinations of those two elements, I make the assumption that it's gonna, at least this point, represent what I need to. So at this assembly, we have a variety of parts. We also have 6061 aluminum for the standoffs. So we're gonna add this one. And it's a nice analysis to perform because we have a mixture of materials. It's not just a simple one. So now we have all the materials. The next thing, of course, is to define the material to the part. So in order to do so, I will create a section and I will start by selecting part and define the carbon fiber. And this is the selection, and a new part was created. I will hide this one because it's already done. You will select all the aluminum parts and create a section for this. I think this can work. Yeah, cool. And aluminum. Okay. And this is Leo's from the future. I forgot to add the point mass, and I'm doing it right now to the sections. And the battery is about 300 grams. Normally it's 300 to 500 grams for this kind of FPVs. It translates to ton. It's a very good thing to bear in mind that needs to remember that the units, because you can easily get confused and put some numbers and then you say, this thing doesn't add up for me. So yeah, make sure you do that. Let's continue. So what's next? Next, of course, is defining those loads and masses. We do this by constraints. So the first thing is, again, as I initially said, I don't want to have all those unnecessary elements in the system, okay? And they can represent the battery, the flight controller, the VTX, whatever. The additional weight of the system, which is important for a model analysis in specific, and impact analysis, and maybe other type of analysis that we would like to make. So to get as much as we can the reality of things, we create those rigid bodies. These are like remote mass that has the effect on the system in terms of inertia, in terms of stiffness for the system. And this helps us to be more realistic in terms of how the system behave in real life without adding those calculated elements to the system. And at this point, we need to attach the remote mass to an actual surface. So we will do that by specifying a surface, which is this one. And well, I can, well, if it was, let's say, connected in this hole here and this, I would select the holes to be much more representative about how it's connected. The thing is that this is like a more distributed mass of a battery that is a very long battery that goes from one side to the other side and is strapped over here. It's just an additional weight that's it. It can create a little bit of a variation for the frequencies, but again, simplifying things. We are looking for simplifying things at this point. This is a design phase. This is not like a final complete design. So we've created this rigid body, and as you can see, it's getting connected to the frame itself. The next thing is defining the contacts. And to do so, what we do is, first of all, let's define a surface interaction. Okay, what I do here, I created a type of surface interaction. Again, my assumption is that I don't want a penetration between bodies. So I'm creating it as like a hard surface behavior. Okay. And next, this is very nice. I mean, I really like it because at this point, what we need to do, we need to define all those contacts between those, bodies. Here we have a tool that actually it sets automatically for distance of 0.01 and lower angle of 35 degrees, and they group it by, of course, parts. It looks for everything. I use it as it is. Okay, we can select a type of contact, a tie or a contact. The difference in between those two here, and different softwares, they name it differently, but the idea is either these two bodies are fully contact in like bonded, or they have some kind of ability to move in relation to each other. Here, I want to simplify things, so I'm not gonna try to create like the friction dependent connections. I prefer just to keep it simple, and I would say it as a tie, which tie means that these are like fully bonded. And then search. This tool immediately gives me all the surfaces that it sees as potential bondings. And what I see here is I just briefly make sure that nothing was missed out. Okay, so a quick recap of where we're at and what we need to do next. We've created the mesh. We've created those point of interests, remote mass, material, defined all the bodies, interactions, and now I think we're ready to go for the next level, which is creating the actual analysis. And here is something that is interesting. Why is that? Because performing an impact analysis or a model analysis, model analysis is more straightforward, but an impact analysis is something that is more complicated to perform. So there's a nice trick to simplify things. You can use the acceleration and translate it or transform it to a steady state force. Does it represent real life? No. It's a more extreme condition in specific, under specific conditions and with a specific definition of how the impact is applied. In most cases, it should represent like a severe case. Where it doesn't represent severe case, I'm not going to get into details here. If it's just anyone, always welcome to ask. It's where when the profile of the impact is, it falls under the one of the natural frequencies or the dominant frequencies of the system. This is where now it doesn't really represent real life, because we're getting into like amplifying that impact just because it falls under the resonating frequency of the system. So that taken into consideration, in most cases it should be fine. This is what I'm always using as a conceptual design guidelines. So I will take static step. This is what they call here static step, and I'm not going to change anything. I'm just going to set it as it is. Press OK. The first thing, as you remember, well, we need to fix this thing in the world. We'll fix it again at the surface that we defined earlier. And what I mean by saying how I fix it is because there are two ways of fixing a model. Is by fixing it as a fully fixed, all freedom of degrees are deadlocked, and there's like a fixation of a specific axis or a few of them, which means that I can only constrain the translation and not the rotation. If things doesn't add up in the results of the analysis, which happens, and this is, you always need to be judgmental about what you're doing. Okay, never take things for granted. You're doing analysis. This is a tool. This is a guideline. This is not a definitive thing. If something doesn't add up, go back, change the boundary conditions, figure out what you did wrong, or just don't use it if it doesn't make sense to you. Only if the results make sort of sense and correlates with some ideas of reality that you know of, and simple mathematics or physics that you can perform yourself on a paper and a pen calculation, see that you are within the boundaries of where you estimated, then you can continue. Otherwise, you're better off not using it if it doesn't make sense, because garbage in, garbage out. So we fixed it. Let's add the loads. Okay, so now we're done with the fixes. Now we need to create the loads. And we do this this way. We go to loads create, and we have two ways of creating force. The first one is concentrated force. The problem with the concentrated force is that you need to select specific element for concentrated force. And by doing so, it can be very inaccurate about, okay, so which element did I select? Is it symmetrically, not symmetrically? Because we're having a distributed, like a number of areas where we're going to put those loads, because it's a drop test of all of the 4 legs. Therefore, this is less good solution for us. There is another way to do that. There's like a surface traction here. What it does, it select a surface. Let's give an example. The motor number 1. Okay, you see this, and it puts the loads in the center of it. So it distributes the load all across the surface over here, which is what we're looking for. So doing that, we need to apply the load. Going back to the concept of this is a steady state. This is something that we want to apply the load in on a like a constant force, and learn how the system reacts. We're going to apply a 10 G's of the weight of the system on those 4 legs. Okay, and how do we calculate this? We'll just take 1 kilo of the weight, and we just multiply it by 10. So we have a total of 100 newtons. But bear in mind that this is 100 newtons is not per motor, because we have 4 motors. So this has to be distributed over those 4 motors. So we have to divide it to 4 because every motor is going to suffer for the same impact, theoretically. And why minus? Because the coordinate system is facing downwards. So we need to change the direction by minus because we want to have the force facing upwards. And that's it. We created force. And I think we're ready to run this first simulation. Okay, done. Results. Now it's gonna create the results for us. Okay, so what we initially see, we see the displacement of the system. See, well, what interests us at this point is this one, the high stresses that we can identify in our design. So and immediately we get 78 megapascals. Okay, so knowing that the parts are made of carbon fiber, well, you can look it online. Carbon fiber can sustain much more than 78 megapascals. You know, roughly estimating, looking at this, I would also do like a rough calculation of, you know, a bending stress, a beam under bending stress, taking this as a section cut, just to get the numbers in a rough calculation to see that this, you know, this is, you know, on the same area of numbers, making sure that, you know, I got some kind of numbers correct. Plus, this is interesting because what we see here is very high stress on this point. Needs to be careful with this because let's say now this would be like 789 megapascals. Did it fail? No. It's just this is like a very high spot. What interest is like this area. Yes, needs to take into consideration this one here. But this can be also an artifact due to the way it was meshed and the point. And what I would do next in order to eliminate this artifact is to refine the mesh in this area, just specifically this area. Again, what I would do is just make some rough calculations about beam under stress with a section cut. It's a rectangular section cut, so it shouldn't be a problem in the distance. Applying this load, see if I get certain, you know, the same kind of results, and that what it does, it just helps me understand that what I did is actually has some kind of a grip in reality. It provides me better assurance that what I'm doing is on the right direction of doing things, because now I know that the model technically represent something that is close to reality, and if I perform things that I perform things that are more complicated, I will have better assurance that the results that I see are highly like better represent the real use case. Otherwise, if it doesn't match, you know, this is like a very big red flag. I wouldn't continue on doing it and go back and try to understand where did I go wrong, maybe with the fixed point, maybe I don't know where the loads are, maybe even the meshing, maybe a lot of things that can vary about where did I go wrong, contacts, but definitely something that at this point I would check myself. Well, technically looking at these results, I can, you know, I feel very confident in continuing this design if I was the one to design this. And this is the end of this part. And the next thing is to make sure that this design complies with frequencies, or what kind of frequencies this thing can resonate to, because this system has a lot of vibrations, exposed to a lot of vibrations. So the next thing is, of course, doing the model analysis.